Okay, welcome back, everybody. Hope everyone's doing okay. Um, I was looking at our schedule. The rest of the semester, we're getting down to the wire, so to speak. Let me share with you the calendar. If you're today's the 12th. Okay, next Wednesday we have your exam number 4, which covers chapters, excuse me, 10 through 12. Okay. And then what we today, I'm going to do chapter 13. So we got 13, 14, and 15. If you recall, we did 16 during the lab when we did the gas experiment. And so today I will knock off, we'll finish up 13 because it's short. Probably get half through 14. And then 15, again, also is fairly short. So I suspect by the 19th, for sure by the 26th, we'll be done with the lectures. Okay. So what that means is if we get done before the end of the semester for lecture time, I will still be here on Wednesdays and basically be open for a study day. And so you're more than welcome to come in and, with any questions, we can go over the whatever material you need. So anyway, so that's, and then on the 3rd, we had the final regular exam number 5, which encompasses all of the chapters. So that's why I say that definitely by the 26th, we'll be done with all the chapters, the remaining chapters. So the 3rd will probably be a study day. Then also the 10th will be a study day because the final will be that particular Friday, the week of the 8th. We have no lab on the 12th, okay? And we'll be also done with all the labs. Now, I'm not 100%. I got to check with the department. On the 5th, I was told that there may be a lab practical. I did have it on the schedule, which is like a short lab experiment, basically covering all the experiments that we had done. What it is maybe just takes parts of it and you go through the process of repeating that particular experiment. That's what they've done in the past. I'm not 100% on what they're doing this time. So as soon as I get more information, I will let you know. Now, we do have one online lab because of the way they scheduled it, and that is on the 28th, okay? Now, the 28th, if you missed a lab, that's going to be a perfect day. Basically, if you didn't miss a lab, there's no lab for you there. If you miss a lab, that's perfect time to come in and make up that lab. Okay. All right. Let's see. Any questions that you may have concerning what we got left over? So, we're looking at today's today's the 12th. So 1, 2, 3, and 4. 4 weeks left of semester, and then the week of the 8th is the final week. So that's to kind of give you an idea of where we're at. So we're looking at total 5 weeks left. All right, any questions? Okay, which also reminds me, if you have any missing assignments or you haven't done, by all means, they're still open. You can go back and finish them up. What Canvas, if you recall, in the syllabus, Canvas was initially set up to give you a penalty if you submitted it after the due date. Don't know what happened. Canvas wasn't cooperating. the commands to do all that were in, but Canvas is not initiating it. So what that means for you that there's no late penalty for any late assignments with respect to the homework and things of that nature. I will start adding some extra credit. In fact, I'm going to initiate an extra credit with Kahoot. And we'll probably do that during the lab time. So, bring your cell phones on the lab. And basically Kahoot, if you're not familiar with it, you get sent to a particular site, you throw in the code, then we go through questions. First one's going to have about 10 questions, and then I'll answer the questions, and then that would be treated as extra credit. Okay, but we'll do that during the lab time. All right. Any comments, concerns, questions? Oh, we almost have a full house. We're just missing one person. Okay, well, we got done with all the chapters up to 12. Okay, chapter 12, we introduced the concept of the mole, which is an important concept because that allows us to do calculations with respect of going from X grams of reactant to calculate how many grams of a product we're making. And the only way to do this is we have to go through a common factor, which is the mole. Okay, so, and we did introduce in chapter 12 a flow chart where we can go from grams to moles, and we even also introduced molar volume, that we can go from grams to moles to volume if you are at the standard temperature and pressure, and if you're gases. So grams to moles to gram, or volume. So we can go in any direction depending on what the problem requires here. Okay, so let's take a look at what we've been doing so far. We've been given reactions. Okay, we started off with looking at the elements. Now we put the elements together to make compounds. From the compounds, we started to put them together and react with each other to make products. Okay, we talked about the chemical reactions. And during that time, we also talked about balancing these chemical reactions, which again, at that time, I stated that those coefficients would be important down the road, so that we can go from, in this example, from nitrogen oxide, if we need, let me do this for a second. If we needed, let's say, if we needed to make 10 grams of nitrogen dioxide, we may need to calculate, well, how many grams of oxygen do we need? Okay, so our relationship is between oxygen and nitrogen dioxide. And note the coefficient in front, the relationship between the two is a 1-to-2 ratio, okay? And those coefficients came about through balancing this chemical reaction. So it's very important that we balance it correctly, okay? Otherwise, if it wasn't balanced and we assume it was a 1-to-1, then our numbers or calculations would be incorrect, okay? Now here I said nitrogen dioxide, but we can go and figure out, well, how many grams of nitrogen monoxide we have, okay? Or if we start off with 10 grams of nitrogen monoxide, how much oxygen do we need gram-wise? So we have all these particular routes that we can be asked, okay? So then after we did this, like I stated, we wrote the reaction. Reaction could be given in words. So we got nitrogen monoxide in the presence of oxygen yields nitrogen dioxide. Taking the words, we write the reaction. And after we've done that, we balance it, okay? Now, when we look at the coefficients, we can look at the coefficients and say, okay, well, we need for every 2 molecules of nitrogen monoxide, I require 1 molecule of oxygen, which then will react and yield 2 molecules of nitrogen dioxide. That is our ratio, 2:1:2, okay, based on the coefficients. So if we start with any number of molecules of nitrogen monoxide, like 10, well, to maintain that ratio, we're going to need at least 5 molecules of oxygen, which would then yield 10 molecules of nitrogen dioxide. Now, in reality, we're not, when we describe a reaction, we may use the word molecules, but in reality, we're using moles. Remember that 1 mole is equal to 6.02 times 10 to the 23rd units, okay, of whatever we're looking at. The mole is simply a number. So now we can stop using the term molecules and state that 2 moles of nitrogen monoxide require 1 mole of oxygen, which after reaction will yield 2 moles of product, which is nitrogen dioxide, okay? And those coefficients are relationships between nitrogen monoxide and oxygen. It's a 2:1 relationship, okay? The relationship between oxygen and nitrogen dioxide is a 1:2 based on the coefficient. And finally, the one with nitrogen monoxide to the product is a 2:2. Okay, those are the 3 stoichiometric relationships that we'll have for this particular reaction that we can utilize to get us from reactant to product or product to reactant, or from 2 reactants with each other. Okay. The following reaction is nitrogen in the presence of hydrogen yields ammonia. Okay, so we could write that out. We get N2 plus H2 reacts NH3. We balance it. We end up with 1 mole of nitrogen. It requires, at the minimum, 3 moles of hydrogen and 2 moles of to yield 2 moles of ammonia. Okay. All right. So these coefficients, as I stated, gives us the mole ratios that allow us to go from grams of nitrogen to moles of nitrogen to maybe moles of ammonia, and then finally to grams of ammonia. Okay, but all of them have to go through to get to from point A to point B. We need to go through using moles. So let's take this particular reaction here. We have iron 3 oxide reacts in the presence of carbon monoxide to yield iron, okay, and carbon dioxide. Okay, so that is our product. And the mole ratios between product and carbon monoxide is a 1:3, which we can write with iron 3 oxide on top or iron 3 oxide in the bottom. Okay. The other ratio is between, say, iron and carbon monoxide. So we have a total of, let me clear this up. We have the relationship between, let's go from iron 3 oxide to iron. Okay, that's a 1:2 relationship. Iron 3 oxide to carbon dioxide, that is a 1:3 ratio there. We had the relationship between the 2 reactants. That's a 1:3. Okay, So far today, we have a total of 6 individual ratios that we can write with the arrows I just wrote. But then there's also the relationship between carbon monoxide and iron. So that relationship is a 3-to-2 right here. Okay. And then carbon monoxide with carbon dioxide is a 3-to-3. Okay. Furthermore, you do also have a relationship between the products, which is a 2-to-3. So we got 1, 2, 3, 4, 5, 6 relationships, 2 ratios in each one. So you get a total of 12 ratios in this reaction here that one should recognize, because the problem given would be to calculate from point A to point B, which could be any combination of those 12 or those 1, 2, 3, 4, 5, 6 different mole ratio relationships. Okay. All right. So given the first problem, it's asking you how many moles of iron can be formed from 10.2 moles of carbon monoxide. So we're looking simply at the relationship between iron and carbon monoxide. Okay. So the question is, how many moles of iron can be created if we start off with 10.2 moles of carbon monoxide? So all we're concerned about is the relationship between what the product gave us, and that's carbon monoxide and the iron. What is happening with the others, we're not concerned with, okay? Because the question is just simply between CO and Fe. All right, so as we do any problem with respect to going from one unit to the other, if you recall that chapter, okay, and what we did last week with the mole chapter, is we write down what we're given, which is 10.2 moles of carbon monoxide, okay? And we write down what we're looking for, which is moles of iron. That helps us set up our mole ratio properly. So we need carbon monoxide in the denominator and iron in the numerator. Why is that? Because we want carbon monoxide to cancel unit-wise, okay? And the relationship between iron and carbon monoxide is 2-to-3. So you can see how in this particular case that we went from moles of carbon monoxide to moles of iron, okay? Moles of iron. And again, if you recall from the last chapter, that the atomic weights have the units of grams per mole, all the atomic weights. So if you have moles of any element, you can get back to grams of any element. So knowing the moles, the atomic weight of iron can get us from moles of iron to grams of iron, but that's the next step. I'm giving you a heads up, okay? So that's how we set that problem up. And okay, that's just here, there it is right here. So this tells us that if you start off with 10.2 moles of carbon monoxide, you will make 6.8 moles of iron, okay? So let me rehash that. We have 10.2 moles of carbon monoxide. That would generate 6.8 moles of iron. Excuse me, my dog's under my feet here trying to get something. Sorry. Okay. All right. Okay, next example. How many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide? So we are concerned our relationship is between iron 3 oxide and carbon dioxide. And I tend to write it right on the equation so I can know what and whom I'm dealing with. So I got carbon dioxide and iron 3 oxide. If we made 17 moles of carbon dioxide, how many moles of iron 3 oxide we need? Okay. And we do that a lot sometimes in the real lab, if you will, is we need to create X number of product, in this case, carbon dioxide. Well, we need to back calculate, well, how many grams of reactants do we need to make X number of product? And this reaction that you shown here is valid whether you're doing lab scale, small quantities, or you're making industrial quantity material, industrial size. The reaction is still the same, okay? So that's our relationship between the two parties here in the question. So as always, we write down what we're given, 17 moles of carbon dioxide. We know we're gonna have a conversion factor here, but we're looking for moles of iron 3 oxide. Okay, so our factor here would be CO2 in the denominator and iron 2 in the numerator, right? So we can cancel our CO2. So, and that relationship is a 3 carbon dioxide to 1 iron 3 oxide. So you're going to need a third of the moles that you've made there. Okay. So let's clear it up a little bit. See the actual numbers. So we will require 5.7 moles of iron 3 oxide. All right. Let's do another example. Well, you have a reaction here that could be written in words and say sulfur dioxide reacts with oxygen to yield sulfur trioxide. Okay, so you write that out and you get SO2 plus O2 yields SO3. Next thing we do, we balance it. And, we have a dissimilar number here of 3 oxygens on the right and like 4 on the left. So let's find a number that would make things a little equal. So we put a 2 in front of SO3, which then gives us 6 oxygens, but it ups our sulfur to 2. So we put a 2 in front of SO2, and that corrects our oxygen also all included there. So we have a balanced chemical reaction here. We got 2 sulfurs on the left, 2 on the right, 6 oxygen on the left, 6 on the right. Okay, so we are balanced. So now it's asking how many moles of sulfur trioxide will form if 0.165 moles of oxygen react. So we're interested only between the oxygen and the product, okay? And if we start off at 0.165, how many moles of sulfur trioxide will be formed or generated is the question. It's assumed in these type of reactions that the SO2 is you have the sufficient amount. Okay, it's in excess. It's a little bit in excess. You have sufficient of SO2 in there for this reaction to proceed. If you did not, the reaction will proceed, but the amount that you're looking for will be much less. And so when you're given a reaction and you identify who are the key parties in the calculations, everything else is just ignored. Just assume that it's in the correct amount, okay? All right, so we write down what we're given, as always, 0.165 moles of oxygen, moles. Okay. And we have a factor here. We're looking for moles of SO3. Okay. So we got SO3 in the numerator and O2 in the denominator. Our coefficient is 2 to 2. As you can recognize, that's simply a 1-to-1. But I would keep the numbers in there for the coefficient until you're comfortable with recognizing that it's a 1-to-1, even though it's stating 2 to 2. Okay. So that's how you set that up. Check by units. Oxygen's canceled, leaving me with SO2, SO3 sulfur trioxide units. Tells me how to set that up properly. Okay. And so we have, oh, what did I do? 2, did I say 2 to 1? Oh, no wonder my mistake. I was looking at sulfur dioxide. Okay, and that's why I had a 2 to 2 there. But should have been this. This is the 1, 2 to 1. Okay, so it is twice the amount of what I started. So I need, I will make, if I start off with 0.165 of oxygen, moles of this, I will generate 0.33 moles of sulfur dioxide. Okay. All right, now how many moles of sulfur dioxide are needed to make 0.042 moles of sulfur trioxide? Now I'm looking at sulfur dioxide jumped ahead, sulfur dioxide and sulfur trioxide. Now the relationship there is of 2 to 2 or 1 to 1. So you can see that you're going to have the same number there. But let's work through the problem so we can make sure that we set it up properly. So we got 0.042 moles of sulfur trioxide, okay? And we are looking for moles of sulfur dioxide. So SO2 in the numerator, SO3 in the denominator. Okay, here's your 2 to 2, which is a 1 to 1. So we're going to make, the answer is 0.042 moles of sulfur dioxide. Okay. Again, I can't overemphasize setting it up properly like we've been doing with these problems and keeping track of our units. Okay, because sometimes the problems can be overwhelming when you read them and you're like, oh my goodness, you know, where do I start? Well, for any type of problem like that, you know, I break it down into pieces stepwise. Put down what you know, put down what you're looking for. And then once you do that, that should help you with respect to what I need with respect to information to get me to where I need to. And you'll find these type of questions sometimes that are very overwhelming when you get these standard tests, when you go on to get your profession. Let's say you want to go to graduate school, there's a test called the GRE, graduate something, I forget the name. They have some questions there that you read them and they're like totally unrelated. At least it seems that way. And what you need to do is actually just break it down, break that question down into the pieces, and what you know, what information you need to put it together to get to the answer. Okay, and I tell you that here because these problems can be sometimes overwhelming because you look at a reaction, you're given the reaction in words. You got to be able to take those words, convert it to formulas, and write the reaction. Then you got to balance it, and then you find the relationships between each of them, and then be able to calculate grams of point A to grams of point B. Okay. All right. Let me clear this up. Maybe not. Here we go. Okay, so this flow chart breaks it down for you, okay? We're going to combine this flow chart with the flow chart we did last chapter to make one big flow chart to help you out with the problems. But in essence, here's the scenario. you're looking for grams given, okay? Eventually you're looking for grams find or whatever the product is, whether it be reactant or product, to make a difference. Whatever you're looking for, you're looking for something, eventually, since we live in the real world, so to speak, I should say, with respect to chemistry, we don't go in the lab and we weigh out moles of a compound. You've been in the lab, you weigh it in grams. So we need to convert the moles to grams. So up to now, we've just been working with moles, and I get from moles of X to get us to moles of Y. But we just need to add one more step to it. And that extra step is using the molar mass. To refresh your memory, the molar mass is basically the sum of all the atomic weights of all the atoms in a compound, okay? Water, H2O, had a molar mass of 18.02 grams per mole, okay? Why is that? Because to refresh your memory, we have one oxygen. Its atomic weight is 16 for the oxygen, okay? We had two hydrogens. Each one is 1.01, so it's a total of 2.02. So we have a total of 18.02 grams per mole, and that is the molar mass for water. Okay? So we need that information. Here, look at this. This is a ratio. 18.02 grams per mole, or moles on top divided by 18.02 grams. So that ratio allows us to go from grams to moles or moles to gram, okay? So refresh your memory how to determine the molar mass for any compound. All right, so the problem will give you grams given. That's in the problem, okay? Well, with the molar mass, you can convert the grams given to moles. And if you look at the units of molar mass, you'll see I need to invert it, where I got moles in the numerator and grams in the denominator. Because when I divide the grams given by the molar mass, I get moles, okay? Now, based on the chemical reaction, that mole ratio now allows us to determine how many moles of what we're looking for, just like we just finished doing the problems right now. We want the moles from one reactant, 2 moles of product, or vice versa, okay? Once we know the moles that we're looking for, based on the mole ratio, with the molar mass of the compound that we're looking for, we multiply it by the molar mass, and note, we got moles, we multiply by grams over moles, our moles canceled, giving us the units of grams. Here in the beginning, by dividing by the molar mass, we have units of moles. The ultimate point of all this is that we will have at least 3 conversion factors on a row as follows, which will give us the X grams of A, and we'll end up with X grams of B, okay? And I use those in general terms. A, whatever could be reactant or product, to B, whatever we calculate. So we have at least 3 conversion factors. The first one is the molar mass that gets us into moles. The second one is the mole ratio, the MR, that gets us into the moles of what I'm looking for. And then this last factor, again, back to molar mass of the compound we're looking for to get us back into grams, okay? Into grams. Because as I talked about before, if we have this, say, hypothetical equation, to give us, I don't know, 2C plus D, maybe this these 3 B's, okay? And if I needed to go from A to C in our calculation, we couldn't go directly from weight to weight. So if I started off with 10 grams of A, I cannot directly calculate how many grams of C I need, okay? I have to convert the A to moles of A, okay? From the moles of A, I see the relationship of C and A is a 2-to-1, and that gives me the moles of C. And then with the molar mass, this here, from here to here, I need the molar mass of A to give me 2 moles of A. And here, having the molar mass of C gets me into grams of C, okay? So the only way I can get from A to C in this general equation is through moles. Moles is a common unit that I need to use. And this flow chart here puts it all together for you. All right, so we have this reaction here where we have iron 2 oxide, specifically 3 moles of iron 2 oxide, reacting with 2 moles of aluminum to yield 3 moles of iron plus aluminum oxide. Okay. What type of reaction is this? Anybody know? You recognize it? Anybody recognize this reaction? How about a replacement reaction? I'll give you half the hint. Okay, replacement reaction. Which one? Because we had 2 replacement reactions. Which one would this represent? Okay. How about single replacement? Look what's happening. You have an aluminum in the elemental form, which is more reactive than iron, because you have iron in the ionic form. It's a compound. And aluminum is a lot more reactive than iron. And then the next question to ask is aluminum in the ionic form here? And the answer is no. Therefore, reaction proceeds. The aluminum then exchanges places with the iron, and the iron now becomes elemental form. Okay, single replacement reaction. Okay, so the first question is a typical type of question asked. Actually, I gave it the words iron 2 oxide in the presence of aluminum. We actually give you iron and solid iron and aluminum oxide. Okay, and then from that you can write the equation and then balance it. And now we can start doing calculations. Okay, so the question is calculate the mass of iron 3 oxide needed. Okay, so we're talking about this iron 3 oxide needed to react completely with 5.5 grams of aluminum. So we're talking about just the reactants. Okay, so that's a relationship that we're dealing with, which is 3-to-2 as far as iron 3 oxide to aluminum. Okay, we need to determine how much iron 2 oxide is necessary if you have 5.5 grams of aluminum. And this is very typical of type of reactions you do in the lab. You may have, an X amount of aluminum, 5.5 grams, for example, and now you need to calculate, well, how much iron do I need so that all of the aluminum gets reacted, okay? And that's the point. You want to add enough iron 3 oxide in there, the correct amount at the minimum, so that all of the aluminum gets reacted. But you don't want to add too much more, just enough. So you get all the aluminum reacted, which is a good thing because in your product, that aluminum gets converted to iron. So now it's much easier to isolate the iron if you have is the correct amount of iron 2 oxide and ensures that all the aluminum has been removed. Okay. All right. So we start off with writing down what we are given. We're going to need the atomic weights and the, oh, bear with me 1 second, please. I got to stop for 1 minute. Okay, sorry. My dog was tearing up his bed. Okay, so let's continue. And then also we're going to calculate the amount of aluminum oxide produced when you start off with 10.25 grams of aluminum completely. So in this scenario, let me change the color just a bit. Our concern is about the product and aluminum. Okay. And if we start off with 10.25 grams of aluminum, how much aluminum, how many grams of aluminum oxide am I going to make? Okay. All right. So the first example is between the reactants. The second example is between one of the reactants and one of the products. Okay, so the first one, we write down what we are given, 5.5 grams of aluminum. Okay, well, we need to convert that amount of aluminum into moles of aluminum. Okay, so we need the atomic weight. Okay, and that gives us moles of aluminum. The next one is the mole ratio between the iron 2 oxide and aluminum, which is a 3:2. Okay, now as I go along, check your units. Notice the first one, the grams of aluminum cancel, the moles of aluminum cancel. So at this point, unit-wise, you are at moles of iron 2 oxide. Okay. And so now to get to grams of iron 2 oxide, we need the molar mass of iron 2 oxide. So we have an iron, we have oxygen, one of each. Look up the atomic weights of each one. They should tally up to 71.85 grams of iron 2 oxide. Okay. And so that means that you check my units. Notice my units are canceling properly, leaving me with grams, units of iron 2 oxide. And then the rest is plugging into the calculator. So that means that if I start off with 5.5 grams of aluminum, I need to weigh out at the minimum 2.2 grams of iron 2 oxide for this reaction to proceed, such that all the aluminum is used up. Okay, it has reacted completely. So you see how we went from grams of A to grams of B, but we had to go through moles. And we have 3 conversion factors at the minimum. We had the molar mass of aluminum. Okay, we had the mole ratio from the balanced chemical reaction. And then finally, we had the molar mass of iron 2 oxide to get us to grams of iron 2 oxide. and we checked our units as we went along and make sure units cancel out properly. Okay, so we have it all unit-wise, everything cancels out, leaving us with units of grams of iron 2 oxide. And the rest is up to you to plug it into your calculator properly so you get the right value, okay? Don't forget to keep track of your sig figs. Sig figs never end. Sig figs are always in science. And so atomic weights, molar masses are not utilized in determining your sig figs, okay? Because these atomic weights come from the average, the weighted average of all the isotopes for that atom, which were all whole numbers, if you recall. Okay. And so having decimal numbers that are the average of whole numbers infers that there's infinite number of sig figs. So therefore, we don't use atomic weights or molar masses in determining the number of sig figs. Okay. Also, the mole ratio are whole numbers, exact numbers. So again, they don't play a factor. But the weight here, 5.55 grams, that is a factor because it is a measurement, okay? And that means we got 3 sig figs there. And so our answer should have no more than 3 sig figs. Remember, you cannot be more accurate than the accuracy of your measurement that you started off with, or the least accurate measurement. All right, the second part was you're starting with aluminum, 10.25 grams, and now you wanted to calculate how many grams of aluminum oxide you made. Okay, so we continue like we did in the first one. We have our first factor, which gives us moles of aluminum, okay? And then we have the mole ratio that relates the moles of aluminum with aluminum oxide, which was a 2:1. Okay, let's check our units as we proceed. Grams of aluminum cancel, moles of aluminum cancel. We are left with moles of aluminum oxide. Okay, which if that's what the question asked for, we could stop there, but it is not. It asked us to convert that to grams of aluminum oxide. So we need one more factor, which is the molar mass of aluminum oxide. And that is the result, 101.96 is the sum of all the atomic weights from 2 aluminum and 3 oxygen. Okay. And now we check our units. Everything cancels out like it should. We are left with grams of aluminum oxide. So we went from this point to this point. Okay. And we didn't go directly with grams. We went through moles. We have to go through moles. So do the math, plug it into your calculator, and that adds up to 19.375 grams. Okay. So let's put this in perspective and something else I'm going to add here. So theoretically, this is basically a theoretical calculation. Okay. That if I start off with 10 grams of aluminum, 10.25 grams of aluminum, theoretically, I should make a 19.37 grams. Okay. This is our theoretical yield. Excuse my writing here. My wand is not functioning properly. Okay. This is what we calculate in theory of how much material, aluminum oxide, we would make, 19.37 grams. Okay. But you get into the lab, you do the reaction, and you run it through the process of the cleanup, and then you finally end up with a product. And you don't really make 19.37 grams. Maybe you make 10.5 grams, 10.5 grams. One. Okay, so our actual yield, what we call the percent yield, is the actual yield divided by the theoretical yield times 100, okay? And so let's do a quick calculation here. And it's 10.251 divided by 19.37 times 100. So about 54.26. So that would equal to 54.26%. Okay, so and we'll probably do this in the lab also when we get to this experiment, but that's what is how you calculate the percent yield. And ideally, when you're in the lab trying to make a compound, you're trying to get to close to 100%. I think the fact of the matter is that for multiple reasons, you very rarely get to that point. You might get lucky and get close to 90%, which is a good yield. But it can on average 70 to 80%, pretty good yield. Okay, now you can't make more than 19.37 grams because that suggests that you created matter, and that's not the case. So if you get anything over 100%, then one or two things. One, your calculations are incorrect. Go back and check it. Maybe the ratio was incorrect. Like in the middle, instead of a 1:2, for your mole ratio, you used a 1:1. So you can see how your numbers are there, okay? Second of all, your material product might still be wet. You did last week, we had an experiment, where you're trying to get a dry sample to get the weight on that. So it might still be wet, or, you may have measured it incorrectly to begin with, totally. All right, but we do this quite a lot when we are making compounds in the lab. We calculate the percent yield, which is simply the actual yield divided by our theoretical yield, okay? Based on the numbers that we have to work with or we use in the lab. All right, so let's clear this up. All right, so this flow chart puts it all together. Last chapter, we had talked about the molar volume, where at STP, okay, very important, at STP, only at STP, we can do this, and that was at 0 degrees and 1 atmosphere, okay? We can calculate the volume, and only if it's a gas. So the yellow, that only pertains, so, excuse me. We have just talked about going from grams given to grams of what we're looking for. We cannot go directly, okay? But we have to go through moles. So if we're given grams, we need the molar mass, which will give us the moles given. The mole ratio based on the balanced chemical equation gives us the moles we're looking for. And then the molar mass of what we're looking for gives us the grams, okay? If we are dealing with a gas and we are at STP, then we can use this relationship, 22.4 liters per mole, to get us from moles of what we're looking for to maybe the volume of that gas, right? If we're at STP, and if it's a gas. If we're not in those two conditions, STP, and it's a gas, you cannot do the ones in yellow. The yellow you can't calculate that way. You have to use other equations, but that won't work. That relationship won't work, 22.4 liters per mole. Okay, now this is a grams given to looking for grams, but this flow chart puts it all in perspective, hopefully, for you, and be able to go in both directions with it. We're going from here to here, but it's a double arrow, okay? Or we're going from here to here, okay? or from there to over here, okay, or from here over here. Okay, so whichever direction you need to go, this flow chart puts it all together. And if you find yourself you're not, quite sure how to attack the problem, like I stated, write down what you're given unit wise, write down what you need to get to unit wise, and then you use this flow chart to help you set up your factors correctly to get to where you're needing to go with respect to units. Okay. This puts it all together for you for as far as these calculations are concerned. All right, so let's do this particular problem where it says write and balance the reaction of HCl aqueous and solid cobalt. Okay. Furthermore, they're telling you what is the oxidation state of the ion. They have to tell you that because cobalt is a variable oxidation state, and it could be in a number of different oxidation states. Okay, so if you look at the activity series, okay, this will also tell you what type of reaction we are working with here. What type of reaction do you think we're working with here? Of the 6 reactions we talked about, what do you think this reaction is? If I had to name it. Well, certainly somebody must know. We have cobalt plus hydrochloric acid, aqueous.
Combination?
It's not quite. Not quite. Good.
Oh,
good.
single replacement.
Single replacement. There you go. Because if you recall from the activity series, let me pull up my table here. If you look at the activity series, remember that series, it's all related to relative to hydrogen. And hydrogen is either in the ionic form would be H plus, or in the elemental form would be H2 gas. Also, the ones in bold from lithium to sodium react violently with water automatically. But after that, from magnesium up to lead, so from magnesium up to lead, in which I designated as say M, for that metal, call it prime, plus HX, which is an acid, you will always get hydrogen gas, plus you will replace the hydrogen with the metal and form it ionic. So MX, whatever MX, and that's from magnesium to lead. Requires just water itself doesn't react and needs an acid. Okay. After hydrogen, the copper and gold, they're very unreactive. They don't react with anything, even with the hydrochloric acid. And to get them to react, it requires a lot more vigorous acids and combination of acids to get it to react. Okay, so yes, this is a single replacement reaction, and we will write it as cobalt solid plus HCl aqueous. And like I stated, it is hydrogen gas. Okay. Now they're telling you the cobalt, what oxidation number it is. So on the side, I put them together in an ionic form, and then I got the chloride. Okay. I need to put 2 chlorides for every cobalt. So our formula becomes COCl2. Okay. we know the hydrogen is a gas, and the chloride, cobalt chloride, will be soluble based on the solubility rules. If you look up the solubility rules right below the activity series, you'll see that the halides, the chloride, the bromide, the iodides are soluble, except when they're bonded with the metals, the heavy metals of silver, mercury, and lead. Okay, in this case, it is not. So it is soluble, and we write the AQ. Okay. So now I can not worry about that. Put those together. I got the correct formula. I got the formula that was given to me in words written out. Okay, with the right states. Now I need to balance it. So if we look at the chlorides, I got one chloride on the left, two on the right. So if I simply put a 2 in front of hydrochloric acid, that gives me the balances the chlorides, but at the same time, what it does, it balances the hydrogens. And so I'm balanced here. I got one cobalt as a reactant, one cobalt as a product, two hydrogens on the left, two on the right, two chlorides on the left, two on the right. All right, so we have a balanced chemical reaction. Let me clear this and let me write the okay, there we go. Here's the balanced chemical reaction. All right, now they're asking the question, how many liters of gas at STP will form if you start off with 5.5 grams of cobalt? Okay, so keywords here, how many liters of gas? Well, obviously the only gas we're dealing with is hydrogen, okay? And you're starting off with 5 grams of cobalt. So our relationship is simply between, our concern that is in this reaction, the calculation is between the cobalt and the hydrogen gas, okay? And you're further given that you're starting off with 5 grams of cobalt. So how many liters of hydrogen gas is generated? And we are at STP. So noting here, by marking up the reaction with the information I need, it kind of gives me a map of which direction I need to go. I'm told I'm at STP, so that means that this relationship I can use if I need. Liters per 1 mole. Every gas at 0 degrees, STP, standard temperature and pressure, 0 degrees of atmosphere, occupies a volume of 22.4 liters per mole. Okay, so that factor I may need in there. Okay, I'm also going to need the molar mass of, or the atomic weight of cobalt. And that from the periodic table is 58.93 grams per mole. Okay, so I'm putting down here all the information I need, cobalt, and then I'm at an STP, so 22.4 liters per mole. It's another factor I'm going to need in here, and I think I'm ready to go now. Okay, so as we've done before, you write down what you're looking for, what you're given, I should say. So I'm given 5.00 grams of cobalt, and I need to know, way over here, how many liters of H2 gas are being generated. Okay, all right, so the first step is I'm in grams of cobalt. I need to convert that to moles of cobalt. So I need the atomic weight of cobalt. So that is 58.93 grams per 1 mole. Okay, grams of cobalt cancel, so I got that set up. All right, that gives me unit-wise moles of cobalt. It's good, but I need to get to moles of hydrogen. So I get that from a balanced chemical equation, which is simply a 1-to-1, right? We are balanced. There's 1 hydrogen to 1 cobalt. Okay, so cobalt, units of cobalt get canceled, leaving me with the moles of hydrogen gas. So being in moles of hydrogen gas, now I can insert the STP relationship of 22.4 liters per 1 mole. Okay, hydrogen's gas cancels out. So now I have liters, unit-wise liters of hydrogen gas. Okay, so now I can simply do the math, and let's clear this up, and we'll let that's there. There. So at this point, you are at liters of hydrogen gas. So what this states is as follows. If I start off with 5 grams of cobalt, okay, and I add in sufficient amount of hydrochloric acid, I will generate 1.90 liters of hydrogen gas. Okay. Also remember that this unit here, okay, could be a factor in your sig figs, simply because 22.4 liters is a measurement. It's not an exact number, it's a measurement. These are not, the mole ratios between reactants are whole numbers, and we already talked about atomic weight. So those are not used in sig figs, okay? But that one could be. So if your answer, if you were given 5.000 for sig figs, then the 22.4 liters would drive your sig figs, and your answer would still be 1.90. If you were given 5.02, then the 22.4 liters wouldn't be a factor, it'd be 5.2, so your answer would be 1.9 with respect to sig figs, okay? So remember that about the 22.4 liters. It can be a factor in determining sig figs. All right, so now the question is this. If 2.374 liters of hydrogen gas are formed, okay, how many grams of hydrochloric acid reacted? Again, at STP, right? So now you have a reaction that preceded, and you need to back calculate 2.374 liters of hydrogen gas were formed, okay? Now we need to calculate how many grams of HCl was used, how much of it reacted, okay? Our ratios is a 2-to-1. Okay, we're still at STP. So I'm writing down what factors I need. I still need that. I'm going to need my molar mass for HCl, okay, because it's asking me to go give my answer in grams. So HCl is chloride's 35.45, and then add 1.05, so I got 36.46, I believe, grams per mole for HCl. That's my molar mass. Okay, and I think I'm ready to roll. All right, so we write down what we're given. 2.374 liters of H2 gas. Well, our first factor is to convert that volume of H2 gas to moles. So we got 22.4 liters per mole of H2. Okay, so that cancels out my liters. Then that puts me in units of moles of hydrogen gas. I need to get to moles of HCl, hydrochloric acid. So I need my stoichiometric relationship where I got one hydrogen gas for every two HCl. This comes from the balanced chemical equation, 2-to-1 ratio. And that will get me into moles of hydrochloric acid. Finally, multiplying by the atomic weight, the molar mass, I should say, of HCl, will get me into grams of HCl. Okay. All right. Let me clear my mess up and bring the other one a little bit easier to read. So 2.374 liters of hydrogen gas. We are at STP, so we utilize the 22.4 liter per mole relationship, okay, to get us into moles of hydrogen gas. Then we use the stoichiometric relationship between the HCl and hydrogen gas, which is a 2-to-1, coming from the balanced chemical equation. And again, emphasizing canceling my units, it should be written H2 up here, H2, okay? Now I'm in moles of HCl, and I need one more, which would be the atomic weight, the molar mass of hydrochloric acid. One chloride at 35.45, one hydrogen at 1.05 gives a total of 36.46 grams per mole, okay? And that will yield 7.73 grams of hydrochloric acid. Notice that there are 3 sig figs, okay? But we start off with 4 sig figs here, but we have 3 sig figs. And you may ask why? Why? Because again, the 22.4 is a measurement. It only has 3 sig figs, so that in this example, the 22.4 defines how many sig figs you would have at the end of your calculation. And you have 3 sig figs. Okay, be aware of that because sometimes Canvas will offer as an answer 7.730, for example, in this case, which is 4 sig figs, and that would be incorrect because that would be the incorrect number of sig figs that you should report. Again, because that is the least accurate measurement, 22.4. All right, so here's another one, a word problem, which we're going to break it down, break right into an equation. Okay. Saying hydrochloric, notice here they say HCl gas. So we're not dealing with hydrochloric acid. There's a difference. And you'll see that in nomenclature, that when you put an AQ in there, normally hydrochloric acid is a gas. And when you bubble it through water, you form hydrochloric acid. So this is hydrochloric acid. And this is basically hydrogen chloride in water solution. That's what's in your stomach, hydrochloric acid. But when it's in the gas form, its name is hydrogen chloride. Okay. And the same would be true for HBr, be hydrobromic acid versus hydrogen bromide. So HCl gas plus oxygen, which also, as you know, is a gas, produces chlorine gas plus water vapor. So it looks like everything is in the gas phase, okay? So that is the equation from words put into an equation. We need to balance here. So we got 2 chlorides on the right. What if I put 2 on the left? That balances out my HCl, okay? but then I have two oxygens on the left, but two on the right. So let me balance that up. What if I put two waters? That balances my oxygen, but that kicks up my hydrogen from 2 to 4. So I need to put a 4 there, okay, to balance my hydrogen. And then my chlorides get kicked up to 4, so no problem. I put a 2 there in front of chloride. So that should balance everything out. Let me clear my mess out and put the other one in. Okay, there you go. So I got 4 HCl's plus 1 oxygen react to give me 2 Cl's, 2 chlorines, and 2 waters. Okay, and the question is, how many liters of chlorine, so how many liters of chlorine can be formed if 3 liters of oxygen reacted completely at STP? So we're looking at oxygen and chlorine. Okay. All right. So we put down what we're given, right? We got 3 liters of oxygen. We are at STP, so we want to get 2 moles of oxygen. So we got the 22.4 liters per mole relationship. And that gets us into moles of oxygen. Now, the next one is from the balanced chemical equation, which is a 2 to 1. Okay, 2 chlorines to 1 oxygen. That puts us into moles of chlorine. Okay. Now we want to get to liters of chlorine. So again, we go back to the 22.4 liter per mole situation because we are at STP conditions. So after we're done, we do the math. You can see here that it would take, it calculates out to be 6 liters of chlorine are generated if you started off with 3 liters of oxygen and you were at STP. Hopefully you can see a relationship here that you can do a little bit of a shortcut, but it does require, there are requirements. One, that you are at STP, okay? Obviously we are because that's the question. Second of all, everybody has to be in gas form. So we got gas and gas. With that being said, I can just use the stoichiometric relationship between the 2 reactants to do the calculations, but you notice that the 22.4 liters, they cancel out automatically because you're at STP. So the stoichiometric relationship is simply utilized to go from liters of one reactant or one to liters of something else. But only I repeat, if you are at STP and everybody's in the gas form. If you don't see it, then don't do that. Just write it all out completely until you're comfortable in recognizing that you can do that. Okay. All right. Try these at home, or we'll talk about them next time. But the reaction is as follows. Carbon reacts with oxygen to form carbon monoxide. And then that's the reaction. Carbon reacts with oxygen to form carbon monoxide. And then how many liters of carbon monoxide at STP can be formed if you start off with, in one case scenario, if you start off with 15 grams of carbon, okay? And then in the second scenario, if you start off with 20 liters of oxygen. All right, so try this at home. We'll definitely try, we'll bring this back next time we meet and we can go over it. Okay, your answers should come up to, for the first one, 28 liters of carbon monoxide, 40 liters of carbon monoxide. All right, so let me summarize all this because we're essentially done with this chapter. Is the follows. In these mole calculations, we have to go through moles, okay? One, we got to have a balanced chemical equation. Two, we recognize the coefficients, make sure it's balanced, and from the coefficients, recognize the relationships between the reactants and products, or the reactants themselves, or the products themselves, okay? So that we can go from reactants to products, or products to reactants, or reactant to reactant in calculating within themselves. Okay. Once you've done, be able to convert the wording into a chemical reaction formulas, you balance it, and now you can do the calculations. And if you use this flow chart, this will literally help you 100% of getting from point A to point B. Okay. And the key to all this is moles. Moles is a common factor to get us from A to B. Okay. And so to get us from A to B using moles, we need to learn how to determine and calculate their molar mass. It's just a summation of all the atoms in the formula. But before that, we have to make sure we write the formula properly, okay? Because if the formula is not correct, then our molar mass will be incorrect. All right, so that's point number 2, I guess. Number 3 is the mole ratio. That gets us from what we are given, moles given, to moles of what we're looking for. That mole ratio has to come from a balanced chemical equation. If the equation is not balanced, then that mole ratio will be off. And instead of being a 2 to 3 relationship, and you inadvertently balance it incorrectly, maybe do it a 2 to 1, you can see how your calculations are being incorrect. So you're going to make sure your chemical equation is properly balanced. And then again, once you go have that, you can get to what you're looking for with respect to what the problem gave you. And from its molar mass, get to either one or two places. You get to grams, or if you are in STP conditions, STP only, I can't overemphasize that, you can find the volume of that material if it's a gas, okay? And this flow chart is basically your map to get from point A to point B, either in grams or liters, either forward position direction or the reverse direction. Okay. All right. And guess what? Congratulations. We are done with chapter 13. Okay. I tell you what, let's do an early break. And then what I'll do once we come back, we will continue with 14. Okay. So I got, my clock says 1:26. Let's come back at 15 to 2. And then we'll continue with the next chapter. Unless you have some questions, we can go over them. If not, we'll continue with 14. All right. So see you about 15 till. Okay. Let us continue. Any questions before I proceed? Okay. Well, let us continue with the next chapter. Okay. Now, in this particular chapter, what we're working with or dealing with is the concept of intermolecular forces. Okay. Now, if we look at the term that they're utilizing here, let's break it down. Okay. They're using the term inter, TER, the prefix, versus intra. Okay. Now, inter deals with these forces in the molecular scale, these forces with molecules with other molecules of itself or any other molecule. Okay. As compared to intra, which deals with the forces within the molecule, such as what type of bond. Is it a covalent bond? And if it is a covalent bond, is it a polar covalent bond or a non-polar covalent bond? Okay. Or is it an ionic bond? So here we're dealing with ionic bonds, with ionic bonds, and covalent. And of the covalent, recall that we had a polar covalent or a non-polar covalent. And that means that you need to go back and refresh your memory about, first of all, two bonds, the bond types, ionic and covalent. And then within the covalent, refresh your memory about polar versus non-polar, okay? Which is related to the electronegativity of the atoms involved in that bond. If the electronegativity of the two atoms involved in a bond were the same because of their same element, then we ended up with equal sharing of those electrons, and hence we had a nonpolar bond. Okay. If it's not equal sharing, then we had a polar bond. Okay. Also, refresh your memory about polar bonds that are not canceled. In general, pretty much 99.9% of the time, when your molecule has all nonpolar bonds, you end up with a nonpolar molecule. We discussed that aspect too. When your molecule has polar bonds and do not cancel out, we end up with a polar molecule. If the polar bonds cancel each other out because of the direction and they're going in opposite direction, and we did discuss some examples of that happening, we have a nonpolar species. So we need to know that to refresh your memory, because we're going to assign a intermolecular force. And this intermolecular force is how these molecules interact with other molecules and other species in solution or wherever they may be. That, in effect, then determines some physical properties of the whole molecule in general, whether things like boiling point, okay? Why certain molecules have a higher boiling point than others maybe have a lower boiling point. We're going to talk about surface tension, why certain compounds have a lower surface tension than others, and viscosity, how thick something runs, as it flows. Viscosity is a measurement of the resistance to flow. Something that's very viscous flows very readily. Something that is not, like honey, flows slowly. Okay, and all those are related to the inter molecular forces. And we're going to talk about those. Okay. All right. But let's first talk in more detail about the intermolecular forces, the IMF interactions. And here we have an example that I just talked about. Is we have two molecules here in B. Okay. Within the species, within the compound, that bond is an intramolecular force, be it a covalent bond, be it a ionic bond or a polar or nonpolar covalent bond, okay? When they are interacting with others, then we're dealing with the intermolecular forces, okay? And these are the forces with other molecules and how they interact with each other. Now, these forces are not bonds, they're interactions, okay? And they're not as strong as bonds, but nevertheless do have some strength to them. So think of it in terms of, think about two magnets, for example, coming together. They're not, the two magnets that attract each other or held together are not bonded to each other, but they're interacting with each other because of the forces involved of the two magnets. And that's what we're dealing with. Sometimes these forces are pretty strong and sometimes they're very weak, and that affects the overall properties of the molecule. So we will be able to, once we assign a particular force to them, determine a relative comparison of some physical properties. We'll be able to say compound A versus compound B. Compound A will have a higher boiling point, for example, or a higher melting point because of the intermolecular force that we assign to A relative to B, okay? All right. Excuse me. We did talk about the bonds, as I mentioned earlier, what type of bonds. In this example, hydrochloric acid, we have a covalent bond. But because they are two different atoms attached to each other, we have a polar bond because one of them exhibits a higher electronegativity. Okay, a lot of this stuff is coming back. Remember, electronegativity was a measure of the affinity of an atom, which is bonded to another atom, the affinity of pulling the electrons onto itself, okay? When the affinity of that, the electronegativity of the two atoms in the bond is equal, there's equal sharing of that bond. When it's not equal, because one is a lot more electronegative than the other, we form a polar bond. And then further examples of the intermolecular forces within hydrochloric acid, and it's how they interact with each other. Okay, there are four types of intermolecular forces between molecules. Okay. The first type is called the London dispersion forces. And this is the easiest to remember. To whom assign these molecules, this force to. And those are all non-polar molecules, compounds, non-polar molecules. If a molecule is non-polar, then the only force it has is London dispersion forces, which, by the way, is the weakest of the forces, of the four. Okay. Second type. These are called dipole-dipole forces. That is between polar molecules. Now, the example you saw earlier, we had HCl. Okay, HCl has a partial negative and a partial positive because the chloride is a lot more electronegative and is pulling the electrons onto itself much more than the hydrogen. Okay, now, when it interacts with another molecule of hydrochloric acid, note that, of course, the negative and the positive are attracted to each other. Okay, they're not bonded to each other, they're just attracted to each other, much like two magnets, the north and the south pole coming together. Okay. Because of the partial negative and partial positive. And then this is three-dimensionally. Not only is it occurring just in the one-dimensional here, but we live in a three-dimensional world. So only those molecules that are polar have dipole forces. Okay, it's like lighting up two magnets, north south, or multiple magnets, how they all lined up in a series. Yeah. Now, the other type is called hydrogen bridging force. It is a dipole force, but it's a special dipole force. Okay, it only pertains to hydrogens that are bonded to, this one's right here, hydrogens that are bonded to nitrogen or oxygen or fluoride. Okay. Yes, they are it is a dipole force because of the difference in electronegativity between the hydrogen and the nitrogen, oxygen, and fluoride. But because of just those three elements, NOF, nitrogen, oxygen, and fluoride, there is an additional force, has a little bit stronger force, stronger strength, and it is such that it has its own name, and it's called hydrogen bridging force. It used to be called, and it still is in some books, hydrogen bonding. Okay, well, it's not a true bond, so they want to defer from using that term and use what's called hydrogen bridging force. I can't overemphasize the difference between 2 and 3 is as follows. Both of them are dipole forces. Okay, hydrogen bridging force is a dipole force, but the dipole force is a special force, so much so that is given its own name called hydrogen bridging force, but is only attributed to those molecules that have hydrogen bonded to either nitrogen, oxygen, or fluoride. Otherwise, it's a straightforward dipole force. Now, of these three, London is the weakest force. Hydrogen bridging is the strongest force, and the dipole is somewhere in the middle as far as strength. And so with that information, you can infer, if you will, that the amount of energy necessary to break up a hydrogen bridging force would be greater than the amount of energy necessary to break up the other two. With the London dispersion forces, maybe taking the least amount of energy because that is the weakest of the forces. Okay, so hopefully you can start seeing how energy is involved here. Okay, and when we put energy into the system, what we're doing, we're in essence breaking up the intermolecular force that's occurring between molecules. And the stronger that force, the more energy necessary to break up that interaction. And if you think about it, water, for example, H2O, requires to go up to a temperature of 100 degrees Celsius to boil. Okay, 100 degrees Celsius. Because the energy necessary to go from the liquid to the gas phase, all that energy is put into the system, okay, and is breaking up those forces between molecules. And by breaking up those forces, they're separated and they go from the liquid phase into the gas phase. If we compare, let's say, ethanol, which is an alcohol, which also has a similar type of forces as water, specifically hydrogen bridging force, it's about 78 degrees Celsius before it can boil. Okay, and so it requires fairly high temperature, but not as much as water because water's intermolecular forces are much stronger than the ethanol. If you look at, acetone, as you may be familiar with this, it's used as a fingernail polisher remover. I want to say its boiling point are, almost, 40-degree-ish. Need to verify that, but it's very low. You open a bottle of fingernail polish and you can smell it. It evaporates very quickly, okay? Because its intermolecular forces are much weaker, and it doesn't take much energy to get those molecules to separate and break up that interaction, okay? All right, so then finally, the fourth type of energy, intermolecular force, is called the ion dipole force. Now, the main difference between number 4 and the others is for 1 to 3 are covalent compounds. Okay, covalent compounds. With the ion dipole force, that pertains to ionic compounds in H2O, aqueous systems. So you'll see the solvent and you'll see maybe something like sodium chloride and water, okay? Now, the only force involved with this scenario is the ion dipole force. It has nothing to do with 1 to 3, okay? So 1 to 3, strictly covalent compounds, both polar and nonpolar. We're going to learn to assign which one here in a second. And then number 4 only pertains to an ionic compound, which is normally dissolved in the aqueous system in water. All right. So let's talk about the London dispersion forces. Okay, well, the London dispersion forces are pretty much a temporary type of force. Unlike the polar bonds, the polar bonds are permanent. Because of the differences of electronegativity, there is a permanent dipole, a permanent partial negative, a permanent partial positive side on those molecules. With London dispersion forces, they are temporary forces because they come from nonpolar molecules. Nonpolar molecules, again, meaning there's no partial negative, partial positive side, but they do create a temporary partial and a temporary negative, okay? Because the best example here, and I wish I had a balloon with me, but I'm sure you tried this. Somebody raised their hand. I got somebody raise their hand. Did you have a question? No? Okay, for some reason I got raised my hand. Notation from my end. All right, well. Let's go back to talking about this. Okay, these are temporary forces. And I'm trying to use an example for you that you can relate to. I'm sure you've seen this, either done it yourself or have someone else do it with a balloon. You take a balloon, okay, blow it up, right? Then you take it and you rub it on your head, okay? Well, what you're doing is all around us, there are electrons. Electrons all around us. That's why next time you walk through thick carpet and then you touch metal or touch somebody, you get a bzz, that's electrons flowing through your body. So there are electrons on your hair. Sometimes there's more electrons than that you want because you end up with a bad hair day. Okay, your hair's got poof. All right, take the balloon, rub the balloon on your head. You, in essence, have transferred electrons from your head onto the surface of the balloon. Remember, electrons are negative charge. Now, if you take that balloon and you bring it to your chest, okay, or someone else's, and very carefully let go of it, guess what? That balloon sticks to them. Okay. Now, why is that? Because you have, in essence, created a temporary partial negative and partial positive area. When that balloon has been rubbed on your head, you have put electrons on the surface of the balloon which have a negative charge. Okay. As you bring that balloon to your chest, on the surface of your chest, there are electrons there too. Well, they're negative in charge, in their charge. Negative and negatives repel, just like positive and positive. So when you bring that balloon closer and closer to your chest, those electrons on the surface get repelled to the electrons on the balloon, and they kind of go in, if you will, creating an area on the body which is partially positive because there's less electron density. That partial positive area then attracts the negative area of the balloon, and hence they attach to each other. Your balloon sticks to your body. Now, it's not going to stick there very long. It will then eventually go back to the stable state. You lose electrons and the balloon falls off. Okay. But these are temporary forces, and they only occur between nonpolar molecules. So that's why it's important to, when you're given a molecule, to determine whether that molecule is nonpolar. Because once you determine it's nonpolar, the only force they have is the London dispersion force to work with. Okay. Now, obviously, the bigger the molecule, the bigger the nonpolar molecule is, the stronger the more London force it has, because there's just simply more electrons. So if I have a nonpolar molecule, this size, and I have a nonpolar molecule this size, well, obviously the one this size will have a lot more London dispersion forces than the smaller one, simply because it has more electrons on its surface. Okay, and this kind of shows you what I just was kind of trying to demonstrate with respect to the balloon scenario. So you got two nonpolar molecules coming together. They got electron density around it. You end up generating a partial positive right here and negative area. Okay, which in effect then creates this interaction, this intermolecular force, this IMF, which is called the London dispersion forces. And they're very weak, they're temporary, and doesn't take a lot of energy to break that interaction apart. Okay. Now, with respect to dipole-dipole forces, here we have a polar molecule, okay? Automatically a polar molecule. Now, we have a partial permanent, partial positive, and partial negative on the molecule. So going back to the example of hydrochloric acid, okay, you have the partial negative, which is going to attract the partial positive of another molecule of hydrochloric acid, creating this interaction right here, this force, which is called the dipole-dipole force, denoted here by the dotted line. Okay. So in order to break up that interaction, it would take a little more energy than it would with the London dispersion, because the London dispersion force is a little bit weaker. Okay. But nevertheless, it would take energy to break up the interaction. Now we show you this picture here, just one dimensional, but again, we live in a three-dimensional world. So, if you can picture these molecules all around, X, Y, and the Z axis. So there's a lot of forces involved in, not just in one direction, but in all three directions. Right? And that force, again, depending on the molecule, can be very strong. All right, now, let me clear this up. what is required to be assigned a dipole-dipole force? They obviously going to be a polar molecule. Now, let's refresh our memory about compounds that had polar bonds, but because of the orientation of those polar bonds, they cancel each other out, resulted in a nonpolar molecule. For example, if you recall, we had, this might require you to go refresh your memory also on the Lewis dot structures. When we generated the Lewis dot structure for carbon dioxide, CO2, we came up with the following geometry. Okay, it was linear. General formula was AB2. Okay, now, can you recognize here between the carbon and oxygen, we have a polar bond. And because of the electronegativity for oxygen being greater, that polar bond is pulling the electron density away from the carbon toward the oxygen. So we have a partial negative on the oxygen and a partial positive on the carbon. Okay, and this is going to the right direction. On the other side of the molecule, we have a similar pattern going on because we have another polar bond between the carbon and the oxygen, which again, also because of the electronegativity difference between carbon and oxygen being the more electronegative is pulling the electron density onto itself more so than a carbon, producing a partial negative on the oxygen on the left. Okay, so we have two polar bonds. And you would think, okay, I got polar bonds, means that I got a polar molecule, but that's not the case here. Because these polar bonds are going in opposite direction, they cancel each other out. So the magnitude of the polar bond to the right, which is a positive magnitude, versus the magnitude of the polar bond to the left, which is a negative magnitude, cancel each other out, resulting in a zero polar bond, net zero, which results in a non-polar molecule for carbon dioxide, which then we assign to it the London dispersion forces. Okay. All right. The other example with respect to polar bonds in geometry, I believe we did the sulfur dioxide, which when we did the Lewis dot structure on that, we ended up again with two polar bonds, no questions there, from the sulfur to the oxygen, again going to the oxygen, partial negative on the oxygen, partial positive on the sulfur. And then the other end, similar scenario, partial positive on the sulfur, partial negative on the oxygen. But note the direction of the polar bonds. They're not opposite in each other. They're in totally different directions that do not cancel out, resulting in a polar molecule, because the polar bonds did not, I repeat, did not cancel out. And we can assign the dipole-dipole force to this molecule SO2 because it has nothing to do with hydrogen. So it's simply a straightforward dipole-dipole force as far as the intramolecular forces involved. All right. Now, the special one that dealt with hydrogen bridging force. Yes, that is a dipole force. As you can see from the diagram here, we're using water as an example, okay? So there is a partial positive on the hydrogen and a partial negative on the oxygen. But because it is hydrogen bonded to oxygen, it has a special dipole-dipole force that has its own name, and it's called hydrogen bridging bonding, or it used to be called bonding, but you're trying to do away with bonding because it's not a true bond. It's an attraction, an interaction between molecules, okay? And this is called hydrogen bridging force. This is by far the stronger of those three forces. Okay. And the thing to remember about that is this one is it is hydrogen bonded to either fluoride, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen. Okay. Only those examples that you have a hydrogen bridging force. And it's right here. This is that force. And which is much stronger than the dipole-dipole force, which is much stronger than the London dispersion forces. Okay. All right. Now, you can see again, we tend to show pictures two-dimensional, okay, but we live in a three-dimensional plane world, right? So these forces, these interactions are occurring all around the water molecule, with water molecules above, below, left and right, and so forth. So there's a lot of interaction going on, okay? Now, again, as I stated earlier, at least the slides did, these are forces that they're strong, but not as strong as an actual bond, either covalent or ionic bond. Okay, so we're not breaking bonds here. Okay, we're just breaking forces, much like a magnet. We've got two magnets that come together. You know, they did not mesh and form one magnet. They're still separated. And so when we pull them apart, we're just breaking apart the interaction between the two magnets that hold each other together, and we're just breaking apart. Some magnets are refrigerator magnets, if you will. This is the best analogy for all these forces. They're refrigerator magnets that take a little bit of force to separate, okay, like a refrigerator magnet, or hydrogen bridging can be equated to strong, much stronger magnets, some super magnets that take a lot of force to break apart. Okay. And that could be equated to hydrogen bridging being the strongest. And then London forces could be equated to refrigerator magnets that are pretty weak. And then dipole somewhere in the middle. Okay. All right. Then finally, the last one, number 4, which is the ion dipole force. This has to do with aqueous systems. Okay. And so if you're asked about this, you know, the requirement would be you got to have an ionic compound and you got to have an aqueous system. Right. So, you know, you have the sodium ion, you got a full-fledged, recall that these ions totally dissociate. These are covalent compounds, ionic compounds, excuse me. When they go in water, they completely dissociate, or maybe don't associate completely, but do to a lesser extent. But nevertheless, there's ions in the water. And these ions are totally stabilized with the water molecules. They're solvated, as they call it, around the molecule, around the ion. So if you look at sodium ion, you can see that the sodium ion is in the middle here. And these water molecules are they're partial negative, the oxygen part. The partial negative is interacting with the ions. Okay, the cations specifically. Okay. On the other side, if this was, let's say, sodium chloride table saw, well, the chloride would be over here, and then the partial positive side is interacting, of the water molecules interacting with the chloride. So they kind of locked all these ions in solution, and they kind of locked them in position because they're being held in place with their being solvated completely with the water molecule. Okay, but the takeaway from here is as follows: that in order to have an ion dipole force, you have some type of ions in solution, which means they're coming from ionic compounds. And you got to have, most of the time, 99% of the time, we're dealing with an aqueous system. Okay, aqueous system. All right, so let's kind of put everything together here, because we're going to talk about the bonds versus the forces. Now, we talked at length about bonds. We touched on ionic bonds, which is a combination of metal, non-metal, okay? Specific ions with a full charge, full positive, full negative charge. They're being held together like two magnets are being attracted to each other, okay? Then we have covalent bonds, polar covalent bonds, where we had an unequal sharing of electrons, okay? And that was because of the differences in electronegativity of the atoms in that are associated in that bond. If the electronegativity is the same, then we ended up with a nonpolar covalent bond, okay? And if they're not, then it is a polar covalent bond. Now, with respect to the forces, there's 4 types of forces. One, the London forces that are assigned to nonpolar molecules. All right, so any compound that ends up with nonpolar molecules because they have nonpolar bonds is assigned the London dispersion forces. Or any compounds that have polar bonds that cancel out, resulting in a nonpolar molecule, have assigned to him as London dispersion forces, okay? All the other compounds are polar. So we have one set of polar bonds, polar molecules that are assigned to dipole-dipole, okay? If there is a hydrogen involved with being bonded with either nitrogen, oxygen, or fluoride, we give it a special dipole-dipole force, and it's called the hydrogen bridging force. Okay, so dipole-dipole, hydrogen bridging forces, we're talking about polar bonds. But with hydrogen bridging force, we're talking specifically about hydrogen bonded to either nitrogen, oxygen, or fluoride. And then finally, we got the ion dipole force, which is an ion in some polar molecule, which in most of the time, like I stated, is water and ionic compounds, okay? All right, now, the forces the intermolecular forces deal with molecules interacting with other molecules, either of itself or some other molecule, okay? Those are intermolecular forces. This is where we need to distinguish. These are inter. The intra are forces within the molecule, basically, essentially the bonds that hold everybody together, that hold the molecule together, be it ionic bond, be it a polar covalent bond, be it a nonpolar covalent bond. Has nothing to do with forces of interactions with other molecules. Okay? And so we need to distinguish the two because questions could be asked, and how you read the question can determine whether you're dealing with intra or inter forces. All right. Okay, now you may be given a list of chemicals here, compounds, and being asked, okay, first of all, is it polar or non-polar? And then once we determine that, we're able to assign to it the strongest intermolecular force for that particular molecule, okay? Now, to determine whether it's polar or non-polar, we may at times have to go back and draw the Lewis dot structure, okay? So we can get a 3-dimensional picture, because if there is a bond, a polar bond, we have to be sure that the polar bonds do not cancel out. Otherwise, if we don't know that information, we can inadvertently assign bonds that do cancel out and assign them to be polar, and that would be incorrect. All right, so carbon dioxide. Okay, well, first things first, we need to determine whether that is polar, nonpolar, and that's the example that we did. Let me change the color here. Where we did the Lewis dot structure, and we ended up with this structure. And we analyzed it, and determined that we have two polar bonds, but since they cancel each other out, we have an overall nonpolar molecule. Okay. Remember that chapter when we were doing Lewis dot structures, and then we were asked to assign whether that molecule was polar or nonpolar? Well, refresh your memory next. You need it here. Okay. So you can be able to assign to it a force. So everything's interconnected. We try to connect everything together here toward the end so we can put everything together and see how things work. So let's assign that, and that is nonpolar. Okay. And it's nonpolar simply because the polar bonds cancel each other out. The fact that it's nonpolar automatically tells us that the only strongest force they have are the London dispersion forces. Okay. PF3. Well, PF3, you may not know if it's polar or not. Okay. But you need to figure out the structure. And when we do that, it's very similar to ammonia. Okay, doing the Lewis dot structure. And once we did that, if you recall, when we were doing Lewis dot structures, and I said, whenever you end up with a lone pair on the central atom, you're either going to have one or two, makes no difference, one or two. Anytime you have a lone pair in the central atom, and you can only determine that by figuring out the Lewis dot structure, okay, which is based on the valence electrons. You know, we go back and refresh your memory how you did that. And you got a lone pair on there, you got a polar molecule, okay? So we can eliminate two of the four forces. We can eliminate London forces, and we can eliminate the ion dipole forces, okay? So for this one, eliminate the London, because that's only good for polar species, and the ion dipole. Okay, the ion dipole we can eliminate. Why? Because there's no mention of ions here. So the only thing left, I see I'm going through a process of elimination here. We got dipole, and hydrogen bridging force. Question is which one it is. Well, we can eliminate hydrogen bridging force. Why? Because there's no hydrogen. It's just phosphorus and fluorine. So the only force left over is the dipole. Okay. Let me regroup here and do that again. Okay. Approach through, you're given the molecule. Okay. You're asked to determine whether it's polar or nonpolar. Well, you may not know what it is, so you go back and do the Lewis dot structure. From that information, you end up with a lone pair on the central atom, which tells you the fact that it's got a lone pair, we have a polar molecule, okay? We got three polar bonds that do not cancel each other out because that lone pair takes up more space and it pushes those polar bonds down so they don't cancel each other out. If those polar bonds were able to cancel each other out, then we end up with a nonpolar species, okay? Once we know that it's polar, we can eliminate the London and the ion dipole force. Boom. That leaves us with dipole or hydrogen bridging. Well, HBF has to deal when you have hydrogen. So we can eliminate HBF. So the only force left over is a dipole. Okay? All right. Just run through the same thing with the next one, HF. HF right there, you don't have to do the Lewis dot structure. You know automatically hopefully that you have a polar species. Why? Because you have two atoms that are dissimilar. Okay? And it's not carbon hydrogen. If it were carbon hydrogen, then it would be a nonpolar bond. Remember that one? So I stated that the electronegativity between carbon and hydrogen is very similar. So for all intents and purposes, it's a nonpolar bond. So that means every other combination, binary combination of two different elements makes it a polar bond. So HF automatically is a polar bond. Okay. So again, we can eliminate London dispersion forces and we can eliminate ion dipole. Okay, because there's no mention of ions here, ionic compounds. So we're left with dipole or hydrogen bridging. Well, here's the interesting part. Recall that hydrogen bridging only pertains to those molecules that have nitrogen, hydrogen bonded to nitrogen, oxygen, and fluoride, of which this is. Okay, so in this scenario, we can eliminate the dipole. So this force for HF would be hydrogen bridging force. Okay. The next one, CH4. This again, hopefully, should be an automatic thing because all you see here is carbon and hydrogen, which is a hydrocarbon, and all hydrocarbons are nonpolar. Okay, let me repeat that. All hydrocarbons are nonpolar. Why? Because the carbon-hydrogen bond is a nonpolar bond, because the electronegativity of the two is essentially the same. Okay, so they are a nonpolar species, meaning that the whole molecule is nonpolar. So CF4, which could be any hydrocarbon of any number of carbon, any number of hydrogens, automatically nonpolar. Okay, being nonpolar, you don't have to go through a process of elimination because there's only one force to assign it, and that would be London dispersion forces. Okay, and then finally you have potassium iodide. The fact that you see potassium iodide, that you see an AQ there, meaning it's an aqueous solution. London dipole hydrogen bridging forces play no part here. There's only one force involved here. It's an ionic compound in water, so the only force is the ion dipole force for them. So you got the water molecule enveloping the potassium and the iodide ions in water. Okay, solvating them. Okay, so what was done here is you're given a formula, some compounds, asked to determine whether it's polar or nonpolar, from which you did that from maybe having to use the Lewis-Dot structure, okay, to determine whether it's polar or nonpolar. Okay, once we assign the polarity, if it shows up to be nonpolar, automatically London dispersion forces. If it is polar, then we have to determine, is it a dipole or hydrogen bridging? Well, if hydrogen's involved and it's hydrogen's bonded to nitrogen, oxygen, or fluoride, then it goes automatically to hydrogen bridging force. Otherwise, it goes to dipole. Okay. And then anytime you see an ionic compound, an aqueous system, there's only one force, and that is ion dipole. Okay. Now we can start assigning or doing some relative comparisons. Now, we can't assign absolute values to some physical properties. We can't do that. But we can do a compare and contrast when we have two molecules, and we can ask the questions about, okay, who's going to boil at a higher temperature, which molecule, okay? And to do that, we have to go through the series here of what we just did and assign to it a intermolecular force, okay? And when we do comparison with physical properties, we're only comparing the covalent compounds. The ion dipole has no part in that. So what we got here is this. The hydrogen bridging force is the strongest of the three forces. So if we were just looking at BP, which is called boiling point, that is a temperature that a compound goes from, say, solid and liquid to gas phase. That is the temperature that it starts to boil. We will see that HF would have the highest boiling point compared to the other compounds, because they have the strongest force. Okay, and equate that back to the magnets, the refrigerator magnets, the regular magnets, and then the super strong magnets. Okay, and you are energy, and you're putting energy to separate them. Maybe I got two refrigerator magnets together. So obviously the refrigerator magnets coming together, attach to each other, but very easily pull apart. Okay, not a lot of energy. The super magnets take a lot of force to pull them apart. So you can equate that to hydrogen bridging force, a lot of force. So I need to put more energy into the system to get them to separate. Compared to the refrigerator magnets, they have the weakest. And we can equate those to the London forces. Those will have the lowest amount of energy required to separate them, and therefore will have the lowest boiling point. Okay, and then the one someplace in the middle will be the one with the dipole force. Okay, we can, like I said, we're not assigning absolute numbers, but we're just doing a comparison. Okay, and then boiling point is just one physical property. We can use, we're going to talk about three other physical properties that some already talk about: viscosity, surface tension, and one more. Okay, but those are all determined, are affected by these intermolecular forces. All right, so let me do this. I got 240. Let us stop it here in slide 15. Okay, we'll finish. And we'll continue with this. There's a question. Okay, no worry, Ellie. We're gonna call it quits anyway. All right, so let us stop the share.